Have you ever wondered how advanced designers model very complex forms in Revit? Hi, my name is Kevin Grenling, and I am a project manager at HPI Architecture, as well as an adjunct professor of architecture at Mount San Antonio College. And I'm here to tell you how Dynamo is an extremely powerful visual programming plugin for Revit that unleashes its users into the API to harness its generative design methodologies. Some of the major topics that we'll cover in this course include a thorough look at the Dynamo user interface and functions, an in-depth exploration of data types and lists, focusing on how information flows through the Dynamo program, an applied exercise constructing geometry with a data-centric approach, and a brief summation of how geometry exists in Dynamo and is published into Revit. By the end of this course, you'll know how to navigate the visual programming environment. Most notably, you'll have a firm understanding of the structure of geometrical data and how to reorganize that data when necessary for construction. From here, you'll be able to explore your own simple structures with the assistance of the many resources presented throughout the course. I'm looking forward to teaching you about the basics of visual programming for Dynamo and Revit, and I hope to see you inside the course. Hello and welcome to your introduction to visual programming with Dynamo and Revit. My name is Kevin Grenling. I'll be the author for this course. Module 1 is entitled, What is Dynamo? Throughout this course, we are going to pursue ways to define visual programming and what it means for us, the average Revit user. We will also get a thorough understanding of the Dynamo user interface, hopefully to a point where we can use it on a day-to-day basis. Additionally, we'll learn to differentiate between static and parametric features in both Revit and Dynamo. If we peek behind the curtain of the software that we use on a day-to-day basis, it's really just a couple of lines of code that are continually executing the commands that we give it. Those commands are realized through a graphics processor, which shows us the imagery that we work with every day. Now, the very useful thing that Dynamo does for us is it gives us a way to transition the code that's operating behind the curtain into a visual display that we can wire together in clever ways and formats to create algorithms. These algorithms are further used to develop geometry. Dynamo then takes our algorithmic relationships, our modification to the code, and feeds it back into the program itself, which generates, of course, the project that we've designed. In case you might be wondering, visual programming really isn't just limited to Revit with Dynamo. There are examples of visual programming in almost every software that we use nowadays. One of the first primary examples of visual programming was Excel. Excel basically is a grouping of rows and columns with data. That data is wrapped together into different formulaic relationships, which is essentially just another way for displaying algorithms. For us, in the architecture and design industry, there are a few different programs that we use typically. In modeling, we use Rhino, we use Revit, SketchUp, 3D Max. All of these programs, in one way or another, have some kind of visual programming component. In video games, we have Unity. The way that we map relationships and actions and all of the playable features of a video game is actually done with visual programming, like you see here. In Grasshopper, which is more of a conceptual design modeler, Grasshopper is for Rhino, and it generates geometry and then pushes that geometry back out into Rhino. For us, when we're using Dynamo, Dynamo will actually generate different geometry, the relationships of how we're tying geometry to one another, where we can modify parameters, and a number of different things that we'll explore in this course. So that said, let's look at what it takes to really operate Dynamo. I have two primary pieces of advice for those of us who are the average Revit user, not necessarily having any experience with computer programming languages or anything like that. The first is begin with the end in mind. Have a little bit of a conversation with yourself or your coworkers about what the product is that you're trying to create. It'll help you identify the various components and tools that you'll need in order to generate that form. Secondly, experience is certainly paramount to creativity. This is not the kind of program that one can pick up and begin using after maybe an hour or so of playing around on a couple of YouTube channels. It's an extremely powerful software, which means creativity can really be amplified by the power that it provides. However, without knowing the underlying structure of how information is passed through and processed and geometry gets changed and families are assigned, we can't really take advantage of Dynamo in its purest form. Some notes about this course. This course is a beginner level course. We're going to review a little bit about Revit, the functions in Revit that are parametric, how we can translate those into Dynamo to be even more powerful parametric relationships, or in this case, algorithmic relationships. The first part of this course is going to contain a lot of data-centric design. And by that, I mean we're going to look at how information actually flows through the program in order to create geometry. At the base level of things, we're going to start off with points and lines or curves and creating some plane relationships within that. Also, something to note is the geometry that we're creating for this course is heavily simplified. In order to understand the software and move on to a more advanced level, you truly have to have a firm working understanding of how data flows. And so we're not going to worry necessarily about the details of hardware or any of the special system families that we would need in order to create full construction documents with this geometry. And for those of you who are Revit users, you're familiar with the visibility settings, and in terms of the level of detail for each of the views, you can think of this course as a course detail exploration. So we're going to look at everything on a general level, and we're not going to get bogged down in specifics at the higher degree of design. This video will review the Revit user interface, as well as introduce the Dynamo user interface. We will also take a look at commonly referenced panels, menus, terminology, and other components that we'll be using throughout this course. Some courses suggested for viewing prior to taking this course would be Introduction to Revit Architecture 2016, Conceptual Massing in Revit, and Structural Trusses in Revit. Not all of these components will be used specifically. However, a working knowledge of the various environments that we'll be using throughout this course would be essential. If you installed Revit per the default installation settings, you'll have an icon on your desktop. For this exercise, we'll be using Autodesk Revit 2016. Once you open the program, you should have a view that looks something like this, which is pretty close to the default. In the top left corner, the Revit symbol will be your access to all of the standard settings: export, save, load, insert. Just to the right of that, you'll have a series of tabs in the dark gray bar: architecture, structure, systems, insert. All of these tabs are going to house panels that organize the tools that we typically use to create geometry. And by geometry, I mean the building components for our design. The large white space that takes up most of the user interface is just that. It's your workspace. This is where all the geometry we're creating is going to be placed, modified. We'll be able to see floor plans, sections, elevations. We'll be able to see 3D views. We'll be able to see legends and schedules. We'll also be able to see our sheets, All of this happens right there in the open white workspace. And if your default settings match mine, you'll have the Properties panel as well as the Project Browser panel on the left side of your screen. If you do not have these two panels, go to the View tab under the Windows panel, and you'll see User Interface on the right side. Under the User Interface icon, you'll see a series of checkboxes that will allow you to either turn on or turn off different dialog boxes that will allow us to control the information that we're working with. It's important to note that when we work in Dynamo, the geometry we're generating isn't necessarily existing in the workspace. That means when I draw four walls or a series of components in Revit, that geometry technically exists in real space, or at least Revit's real space. Let's move into Dynamo now to explore the differences between the two workspaces. In order to install Dynamo, you'll have to download it from the web page. If you go to www.dynamobim.org, you'll be able to click the button in the top right corner which says Download. Once installed, you'll have to restart Revit if you have it open. Once it's restarted, if you go to the Add-ins tab, under the Visual Programming panel, you'll see Dynamo. Click the icon to open it. As I mentioned before, Dynamo is a plugin for Revit, and that means that it's going to open up as a separate window that lives over top of the Revit user interface. The main start screen has a couple of components that we should note. In the top left corner, we're able to create a new file, create custom nodes, or open existing files. Just below that, we have a list of recent files that were opened. And most notably, on the right, there are a couple of components to note here. There's a link to the Dynamo website, there's a link to the Dynamo discussion forum, as well as a series of video tutorials. The primer is there, which has a lot of exercises that one could follow to get a more firm understanding of the program. I would like to make a special note about the Dynamo discussion forum, which is particularly active. The team of developers over at Autodesk are actually quite passionate about what they do. And so one could expect to get a pretty swift response from the team if they post a question there. For this exercise, we're going to start off with a new file. Dynamo will bring you to the workspace. Similar to Revit, the workspace is a wide open area on the right side of the screen with a series of panels and tools on the left side of the screen. In the top left corner, you'll see your standard file edit view where you can save and open new files, where you can find help if you need it. Another thing that I would like to point out especially is the help file. If you click on the help menu and hover over samples, you'll see that there are a series of exercises that you could go through to explore the program further. I would highly suggest doing so. Direct your attention to the left side of the screen for a moment, and let's take a look at what this library panel is. The interesting thing about Dynamo is that the commands are actually based on the .NET framework. For us as your typical Revit user, that doesn't really mean much, but the library bar on the left is an extremely powerful user interface component. This is where we as the user can search through and explore all the different types of tools that Dynamo has. You can see that it's a lot more concise to what you saw in Revit, where it was broken out into tabs and panels and you could visually see the icons for all the tools. Here, it's actually listed much like your file structure. If you click on the arrows on the left side of Analyze Bulletin Core, you can see all the various tools that are available to you, and some of them even have subfolders that you can open up to gain more tools. By expanding the geometry menu, we're able to see that this is going to be where we find most of the typical types of geometry we create. Under operators, we can see that there are a lot of mathematical functions that are available to us as well. This is part of that data-driven component that I mentioned in the previous video. And also, if you open up Revit, it's important to note that there are options to select and modify view settings, analysis tools. You can grab elements directly from the Revit model, and also form and modify views. All of these are just a hint at what Dynamo can actually accomplish and what types of information it can begin to process. The workspace on the right has a couple of different components to note. The first of which, and the most obvious to us as the typical user, is that there's a grid that's in our workspace. This grid is going to be the basis upon which we generate our geometry, the points or the sizes or the direction, anything like that. In the top right corner, you'll see a series of icons. These icons are important for us to understand. When you hover your mouse over the icon that is currently selected as blue, it should say Enable Graph View Navigation. And then hover over the one just to the left of it. And what you'll see is that it says Enable Background 3D Preview Navigation. Now, the 3D preview correlates to this grid that you see in your workspace. In order to truly understand what these two settings are doing for us, we have to first drop in a component as if we're building a definition. Go to the library search bar and type in point. A whole list of different types of points are going to come up and be available to you. However, we are going to select point by coordinates, and Dynamo will place this component into your workspace. In Graph View Navigation, the component actually sits in the workspace, floating above all of the geometry in the back. Click on the component to select it. Click off of the component to deselect it. If you click it and drag it around, it'll move around the workspace. Now notice, when you click on the component, you'll see a couple of arrows, red, blue, and green, have showed up on the point at the origin in the workspace behind our component. That is showing us that our geometry is actually being selected. That geometry exists in the workspace behind the components that we're putting into the workspace. Now, if we click on Enable Background 3D Preview, you'll see that the component itself has actually gone translucent, and the geometry now becomes prominent. So if you do the same kind of navigation exercise, if you zoom by rolling the wheel in and out, you'll be able to see that now you're not just zooming in and out of the components, you're zooming in and out of the geometry instead. The only other added feature when you're working in 3D is that you have the ability to orbit by holding the right-click button down. Additionally, the other way that you can toggle back and forth between your graph view for the components and your 3D view for the actual geometry is by using Control B. These components are preloaded with instructions. If you hover over the title of the component, it'll give you some information about how it calculates the information. So point by coordinates says form a point by 3 Cartesian coordinates. And below that, it tells you that you need to give it an X, a Y, and a Z. But if you hover over X, Y, or Z, you'll see that it also contains a default value. The default value right now is 0, 0, and 0, and that's why our point exists at the origin, where the red axis, the green axis, and the blue axis intersect. Go to your library under the search feature and search for number. The one with the icon that says 1, 2, 3 will be the one that just creates a general number, and we can change it to be whatever we want statically at any particular time. In order to make a connection between these two components, we need to know a little bit about the anatomy of the components themselves. Let's take a look at the number component for a moment. It has a text box in the bottom left corner. It has an arrow on the right side. The text box in the bottom left corner is where we input the information that we want it to read. The arrow on the right side is where we connect or output a wire. It's called an output. If you click on the output and you move your mouse off to the side, it's going to show you that it's an incomplete wire because it's dashed, at least for now. And then click on the X input of the point by coordinates, and then that wire becomes a solid black line, which means it's connected, information is flowing. Now we're able to change the X coordinate of this point by typing in a number, say 10. Behind the graph view, you should see that the point moved from the origin along the red axis, which is our x-axis, a total of 10 units. If you go back to library and search for number again, there's another component that is called number slider. This one's very important because it's going to lead into what we're talking about in the next video, which is the difference between static and parametric features. We're going to look at these two new features once we move into our third video. However, before doing that, let's look at a couple of the notes that we should keep in mind about Revit and Dynamo. Dynamo is an add-in. It's a separate window that lives outside of the Revit user interface. It's important to be aware that Dynamo is constantly updating. The developers are very active. It's an open source software, which means that even the users are generating new tools every day for use. The best thing about the way that they've set up Dynamo for open source use is that it's operable even when it's slightly out of date. So if it's been a couple weeks since you got back into developing a Dynamo definition, it should still be operable even if there were a couple of small package updates. In some instances, when they go from version 8 to version 9, for instance, you may have to upgrade before you're able to produce anything. And a very significant note about troubleshooting. Visual programming is not easy, and I do anticipate that most users, in fact all users, are definitely going to run into an issue where they can't figure out what's going wrong. They have a loop somewhere in the code, or they can't figure out which type of surface to generate in order to import it back into Revit. All of these things can be addressed in the very active community that's present on dynamobim.org/forums. In the next video, we're going to discuss the very intricate differences and likenesses between static and parametric geometry. In this video, we're going to explore the differences between static and parametric features of both Revit and Dynamo. In Revit, examples of static features would be the typical geometry that we create sculpturally as designers, namely the walls, the roofs, floors. All of these things are built by us, and they stay like they were built by us until we specifically modify it otherwise. The parametric features that you would see in Revit would be something like a family, for example, a casework base cabinet. The parametric features of the casework base cabinet are built into reference lines or planes that define relationships from one of the elements in the model to the other elements of the model. So when we change, for example, the height of a base cabinet, the height or depth of the top drawer might stay the same, but the equal distribution of the drawers below will modify to the new height of the base cabinet overall. In Dynamo, what you'll find is that we have static data and parametric data. Static data is information that we feed in on a one-time basis. The parametric part comes into play when we develop an algorithm that further modifies geometry by a set of rules that we define. These can be automated and built off of previous relationships. In order to begin exploring Dynamo and the information that we can process into an algorithm, we have to first understand the types of information that it can read. In the Revit components, you have parameters that are built into your rooms, your sheets, your families, and these take different forms. In these examples, what you can see is that in the rooms and sheets, you have a series of textual as well as numeric data input. In family parameters, you can see that a lot of that information is also textual and numeric. Our first exercise within Dynamo is going to begin with textual data input, and those are called strings. Open up a fresh new file in Dynamo. We'll start this definition with a manual setting to the manual automatic toggle, and let's get to work. The component that we're going to use to produce or generate string information, so this is textual information that's read as text, would be string. So in the library, search for string. The string component is dropped in with a text box on the left-hand side and an output arrow on the right-hand side. We'll need two string components in order to complete a concatenate or concatenation, which will blend the two sentence fragments together into one complete sentence. In the first string component, we'll write the phrase, "the quick brown fox." In the second string component, we'll write the phrase, "jumps over the lazy dog." In order to blend these two sentences together, we'll need the component for concatenation, which is called string.concat. If you just search for string, you can see it down the list, or you could search for concat, and either one will produce the component you're looking for. The icon will say A, B, C in blue, and the title will say concat. When it's dropped in, you'll have a string 0 with a plus and a minus, and then a string on the output side. So the string 0 is the input. The plus and minus will increase or decrease the number of string inputs that it can receive, and then the string output will be the product of the blending of these two sentence fragments. So click on the plus sign once. In the first string input, click on the output of your quick brown fox sentence fragment and plug it into the string 0 input of string concat. In the second string component, this component will be plugged into the string 1 input of string.concat. The last component that I want to show you here for this exercise would be the watch node. The watch node, when you search for it in the library, is described as visualizing the output of the node. There are a couple of different ways of doing this. The watch node makes it readily available to you at all times. Bring the watch node next to the string.concat and connect the string output to the watch input. When you click the Run button next to Manual, you'll see that the two sentence fragments are concatenated or joined to create your complete sentence. The quick brown fox jumps over the lazy dog. The other way of revealing the output of a node is to hover over the gray line that's in the bottom right corner of the string.concat component, and you'll see that the sentence actually shows up below the component, but if you move your mouse away, it disappears. Once you hover over, there's a gray switch that appears on the right side of that sentence below the node. If you click that switch, it becomes a permanent display. If you click it again, it'll turn that display off and it'll hide it once more. Now if you switch your automatic manual toggle over to automatic, we can make a change to the first string, and you'll see that that change is immediately propagated into the watch panel. In the string 0 input string, change it to read "beauty is in the eye." Now you'll see that the watch node actually reads as "beauty is in the eye, jumps over the lazy dog." We'll have to change the second string, so the string 1 input, to read "of the beholder," to complete the sentence, beauty is in the eye of the beholder. Now that we have a firm understanding of automatic and manual data processing and a little bit about textual data input, we need to now look at numerical data input. We're going to do this by also exploring how geometry is published into Revit and why it's so important to begin with the end in mind. For example, if we need to create a curve in Dynamo and then publish that curve to Revit, we'll need the modelCurve.byCurve component. The description when you search for it in the library reads, construct a Revit model curve element from a curve. Now the subtext to this is that it understands a curve to be a Dynamo generated curve data point. Now if we work backwards, this component's structure reads that it has a model curve output and a curve input. Over time, we'll begin to understand more about the different types of geometry that can be converted to read as one another. In this particular case, we can give a line to the curve input, which will read as a curve. If you search for line in the library, you'll see that the first one is by start point endpoint. There are also a number of other different types of lines that we could be interested in, but the start point endpoint line is going to be the simplest for us. It also requires a numerical input in order to provide the location of the points that we need. So once that's in the workspace, we won't connect it yet. We'll also need to generate the location of points that we're going to create our line with. Just like we did in a previous video, the point.byCoordinates component is going to be the one we'll use. Search for point and bring in a byCoordinates point. It will require an X, a Y, and a Z numerical input, and it gives us a point output, which we can connect to the start point and the end point of the line. In this exercise, we're going to create our first point at the origin with a numerical input of 0, 0, 0, and the endpoint will be 10 units off of the origin along the x-axis. So our first point by coordinates will receive an x, y, and z input of 0, and our second by coordinates will receive a y and z input of 0, as well as an x input of 10. Using the numbers node, we can generate a numerical value of 0, as well as a numerical value of 10. Once the numerical inputs are connected to point.byCoordinates, hit run. You'll see that in the background 3D display, the 2 points that we've generated now are shown in the Dynamo user interface background. Once we connect the start point and the end point, Dynamo reveals a line that connects the two. Now, this line does not yet exist in the Revit workspace until we have converted that line to a model curve using the model curve by curve component. So after we connect the line to the curve, hit run for a third time, and in the Revit workspace, we now have a model curve that's readily modifiable. The important thing to note with this is that this geometry is specifically tied to the Dynamo definition. If we select the model curve and move it away from its original position, the Dynamo line is shown, the model curve's new location is shown. However, if we run the Dynamo definition again, it'll return that model curve to its original position. If we delete that model curve and then run the Dynamo definition, it will also regenerate that model curve in its Dynamo defined position. If Dynamo is running in automatic mode, you will be able to select the model curve in Revit, but once you move it or modify it or delete it in any way, it will automatically regenerate via Dynamo and return it to its original position. In this video, we've explored the differences between static and parametric features of Revit and Dynamo. We've looked at the different types of information that Dynamo can read from the Revit environment. We've explored textual data input via a concatenation. That also provided us knowledge in what the difference is between automatic and manual data processing. And we've explored the relationship between geometry that's generated in Dynamo and geometry that lives in Revit using numerical data inputs. And stepping back for a moment, overall in Module 1, what we've explored is that visual programming is a way for us to peek behind the curtain of the software package itself and provide more power for generating algorithmic relationships that enhance our usability of the software. We looked at other examples of software packages that utilize visual programming. We've refreshed ourselves in the Revit user interface and introduced ourselves to the Dynamo user interface and how it processes information. In the next module, entitled Basic Features of Dynamo Form Generation, we'll further expose ourselves to more nodes and components that can be used to generate more intriguing geometry. We'll learn more about file management, how to organize our files, how to write notes about our files, and how to generate more interesting and more complex algorithms for our designs. And very importantly, we'll look at lists and how data is passed through Dynamo at a higher level. Welcome back to Module 2, entitled Basic Features of Dynamo Form Generation. In this module, we're going to look at the various node types that we typically use, as well as the structure of data input, generation, and modification. We'll also explore file organization, file management, and get into our first algorithm creation, and the lists that they generate, which are incredibly important to understand in order to get through the logic and sequencing of the different commands we're trying to execute. And finally, we'll take this knowledge and apply it to generating a simple sine curve. Our first video is going to stay very abstract, and we'll look at the node types and structures and discuss a little bit about file management. To do this, we can start a new file in Revit, as well as open up a new file in Dynamo. Now, in the previous videos, we've already covered the fact that there are static and parametric data inputs. We looked at the number and the number slider, so we'll drop those into the workspace now. We also looked at the string input for text-based data. Each of these three nodes is a simple data input. It will generate at any particular time one number or one string and feed that into an algorithm. Another more dynamic way of accomplishing this task would be through a code block, which is a readily modifiable output node that allows us to capture strings and numerical data in one convenient node. To find it, either go to the library and type in code block, or double-click in your workspace and it should pop right up. The reason this is tied to such a convenient hotkey, the double mouse click, is because a code block is incredibly powerful. The code block not only allows us to put string and numerical data types in as an output, it also allows us to generate Python script that can tap into the API of the program itself. This course will not cover Python programming for Dynamo, but as a basic introduction to this tool, if you, the user, want a string output, simply put whatever you'd like as your string in quotes with a semicolon at the end. Once you click off of the code block, it'll create an output arrow on the right side of the node. Additionally, if I wanted to add in an integer output, I could simply type in the integer and then with a semicolon at the end, once I click off again, you'll see a second output appear. Now I have the ability to tie either my string or my numerical data to any one of the nodes that I put in for my algorithm. Another very simple node that is used quite often is the Boolean node. Now, the description in the library says that it's a selection between true and false. And it takes the form of a toggle where you either click the circle for true or the circle for false. The other way that Boolean figures are sometimes calculated is actually by zeros and ones. I only state this now in the event that you encounter zeros and ones being used as a switching mechanism, which you may find at some point in the future. Those are 5 of probably the most common simple data generators. Some of the more complex data generators would be those that actually tie into either Revit or other files. For example, a file path node, if you search for that in the library, you'll notice that there are a bunch of potential nodes that actually relate to other files. For instance, you have write text, write to file, read text. All of these are designed to allow data to be pushed out of Dynamo, even out of Revit, into something like a CSV file, and then later modified and brought back in and used to actually generate geometry from an external source. Along with that, we have a couple of nodes that could potentially tap into the Revit user interface to pull families or parameters. A good primary example of this would be the categories node. Searching for that in the library and dropping it into the workspace, what you'll see is that it's actually made up of a pull-down menu on the left and then the category output on the right. The pull-down menu on the left is pretty versatile. Any category of family or component that you have loaded into your Revit file will be displayed in this list. For example, you can see just at the top of the list adaptive points, analytical nodes, or even something like an annotation crop. Similarly, there is a node that's called element types. Now, element types are specifically geared toward pulling an element itself. So when we drop that into the workspace, what you'll find is that here we actually have some of the model components that would be sorted into those categories. For example, area, area scheme, analytical link, analytical models. All of these things are the actual objects that live within your model. You won't necessarily need to use these tools in this course. However, I do want you to be aware that that type of information is available to you in this program. Now, before I move on to describing another type of node, I want to first go back into the library and describe something. In the library, expand geometry and scroll down to expand vector. Vector has probably a list of 20 to 30 different nodes within it. However, if you pay attention to the left side of the menu, you'll see that there are symbols with a couple of different colors that represent different types of nodes. If you hover over the plus sign, you'll see that it says Create, which tells us that anything that's to the right of the green bar is designed to create information, whether it's the location of an axis, the direction specifically by coordinates. It will create a vector based off of the coordinates that you give it. Below that, in the red section with the lightning bolt, there are action nodes. And action nodes are what I typically call a modification. For example, once you've actually set the direction of a vector, an action node known as reverse would be able to give you the opposite reaction vector. And last, at the bottom of this list, in the blue section with the question mark, this is called query. Query nodes are designed to either isolate or deconstruct the information that we create into subcomponents that we can then use later on. Now, the idea of constructing geometry or information or deconstructing geometry and information comes into play in a very strong way later. But for now, let's look at a couple of examples of nodes that actually don't start off with raw data. And these would be the nodes that actually receive the information that we've just created. So they have on the left side inputs, and on the right side they have outputs. The first of which is going to be the sequence node. So in library, type in sequence and drop that into your workspace. Its description says that it creates a sequence of numbers. And on the left-hand side, we have a couple of inputs. We have a start, an amount, and a step. And the description as you hover over them says a number or letter to start the sequence. The default value is the number 0. And then at the end, on the right side, we have a new sequence. The amount is quantitative, and so it requires a numerical input. And the step has a numerical value as well to define the space between numbers or letters. It very quickly becomes important to actually read the descriptions when you're dropping in a new or unfamiliar node. Back to the library, let's type in math.sin, S-I-N. When you drop that into the workspace and hover over it, you'll see that it describes it as finding the sine of an angle. On the left, you have an angular input, and on the right, you have the sine output. These are two examples of nodes that are not readily modifiable. They have a set number of data inputs, and they have a set number of data outputs. While we're on the subject of math, let's look at the formula node. The description for the formula node reads, evaluates mathematical formulas. But when you drop it into the workspace, it's pretty barren. To us, the untrained eye, it only looks like the string input or a numerical input. And the truth is, you could treat it sort of like the code block or like a string or numerical input. However, when we type in a mathematical formula using proper syntax, we're able to define the number of and types of data input that we receive, as well as the data output that it produces. To illustrate this, type in a very simple formula, parentheses, x plus y, parentheses, times z. Once you hit enter, you'll see that the x, y, and z inputs are now present on the left side of the formula node, and the output arrow is present on the right side of the node. So once it has its numerical data input, it'll be able to process that like a calculator and give you the numerical output. For our last node in the library, expand core. Under core, expand list. The reason we opened this list instead of searching for it is so that we can see the many different types of list modifications that we can do. List.create is at the top. You can drop that into the workspace now. You'll see that it becomes preloaded with an item 0 on the left as an input, and then a plus and a minus, and then a list output on the right. The description is that it says it makes a new list out of the given inputs. Inputs is plural, but right now we only have one input, and that's where the plus and minus come in. If you click the plus, it will add as many inputs as you need in order to generate a combined list. This node is designed to combine lists, but if you look back in the library, there are almost an infinite number of other ways that we can modify these lists, as I mentioned before. We're going to use some of these in the very near future, but for now, I have to make sure that I can keep my file clean. So this is where the idea of file organization comes into play, because algorithm creation is heavy. Some of the more complex algorithms can have hundreds, if not thousands, of nodes in the workspace that are all wired together like a very intricate electrical system. To manage this, we as the user have tools to leave notes for ourselves. The most simple form of leaving a note is found in the Edit menu under Create Note, or Control W. The note gets dropped into the workspace as a very tiny gray tag. If you double-click it or right-click it and edit, you'll be able to write any note that you need to leave yourself as you're developing the definition. Right now, all of the nodes are visible on screen, so we can see them here and we understand how it's organized. However, once it gets much larger, we're going to have packets of information, some located here, some located off screen somewhere else. In fact, many that are located off screen somewhere else. So these notes serve to remind us of what we designed that particular group of nodes for. And speaking of groups, grouping is one of the most powerful things that we can do to organize our file and keep it readable to other users. So in the top left, I have my manual data input nodes. So if I select them all, I can either hit Control-G or go to the Edit menu and select Create Group. And what you'll see is that a colored box appears around the nodes that you've selected, with some text at the top that says, click here to edit the group title. When you double click, you have the ability to change what that group of nodes is called. I'll call mine Manual Input Nodes, and then click out to accept. And then the other modifications that we should be aware of is that we can change the color and the size of the text. If you right-click on the group, you have a selection of colors that are available to you at the bottom of the menu that pops up. You also have the ability to change your font size by hovering over Font Size and selecting from the list that appears to the side. Depending on how large or small your definition is, it might make sense to use larger text because when you zoom out, you'll be able to see it a little better. In the next few videos, and even more particularly in the next two modules, you'll see me using groups quite exhaustively. It's incredibly important for us to be aware of what the intent was when we developed that particular group of nodes. And for our purposes, I'll call that an idea. An idea is a complete group of nodes that receive data, process it, modify it, and produce an altered set of data that I can then feed into a separate idea. This demonstration video is designed for users to develop a sine curve. Some topics specifically covered would be lists of data, how to patternize a list of data, how to generate mathematical modifiers, and then finally, creating a sine curve from mathematically derived points. Step 1 is to generate a sequence of numbers from 0 to 360. We'll use a separate mathematical system in order to create a mask that will separate our even and odd numbers. From the library, bring in the node called sequence. Sequence is going to be where we input our start number, the amount of numbers, and the step between each number generated. Our static numbers are going to be the start point of 0, the amount of 360, and the step will be number 1. After running the definition, if you hover over sequence, you'll see a preview of the data that it generated. Otherwise, you can add a watch node and view it from that location. Our goal here is to filter out the odd or the even numbers in order to generate separate lists. To do this, we will use the list.filterByBool mask. Its description says that it filters a sequence by looking up corresponding indices in a separate list of Booleans. On the left, we have the list that it requires, which would be the numbers we just generated. And below that, it says mask. And the mask is described as Booleans. This is an example of beginning with the end in mind from Module 1. Our objective is to find a node that will generate a Boolean mask list. It takes a lot of experience to really know off the top of your head where these come from. The one that we will use is a testing operator that says equal to x, y. That tests whether or not the x input or list of inputs is equal to the y input. This is found by searching for equal equal or going to the operators list in your library. Similarly, I can test whether or not my original list of numbers is divisible by a certain numerical integer. With equal equal, I have to test whether or not something is equal to y. I can't yet plug in my original numerical list into the x and test it against y because every individual number is unique. However, if I use in the operators menu the is x divisible by y node, I can test that entire list of numbers to see whether or not it is odd or even. If my list is divisible by, say, 2, then the output would be a measure of whether or not it's odd or even. That output, after you run the definition with your sequence connected and 2 going to the y, that output will give you a list of zeros and ones. That list of zeros and ones can be measured for equality with the number 0 as your y input, which, when run, will produce your true and your false, otherwise known as your Boolean list, which would be your mask for your list filter. Plug a watch node in to the in or the out or both of the Boolean mask, and you'll see that your odd numbers and your even numbers are now separated. Now that this idea is complete, I'm going to group it and name it odd/even test. My next and final exploration in this module is going to begin with the same sequence that I've already generated. Select the numerical inputs as well as the sequence nodes from the group and copy and paste them to an area below. To generate the sine curve, we're going to use the node known as polycurve by points. My typical workflow usually includes placing these nodes on the right side so that I can work left to right in order to fill in the gaps and make the connections. Polycurve by points has two separate inputs. It has a list of points and it has a Boolean input to determine whether or not the end of the polycurve needs to return back to the first point. The default for this is set to false, which is what we want for our exploration today. Considering the fact that polycurve by points requires points, I'll need a node that will generate those points. Point by coordinates will require an x, a y, and a z axis in order to create a group or list of points. For my exploration, I could plug this sequence into the x input directly. However, my numerical values are of a range from 0 to 360. Dynamo borrows its units from Revit. So if I plug in my points in the x direction up to 360, that means that my overall sine curve is going to be 360 feet long. For me right now, that's kind of undesirable. So what I'll do in order to limit the maximum length that this sine curve can be is I'll just throw on a conversion from degrees to radians, which in this case is really just meant to filter out the larger numbers and bring everything down to a lower level. We could also do this with simple division. In order to get a properly graphable x position for all of the points in my sequence, I have to filter them through a degrees to radians conversion. Math.degrees to radians is going to allow us to delimit our graph extents. By filtering the sequence through the degrees to radians conversion and connecting it to the x input, we've settled all of our x coordinate requirements. The y coordinate is where the sine mathematical operator is going to be plugged in. Once you've brought the sine node into the workspace, you'll see that it requires an angle on the left and produces the product of the sine on the right. In reality, we could just plug in the sequence directly into the angle, and then the sine directly into the point by coordinates y input. However, I want to be able to parametrically modify the wavelength of this sine curve. I can do that by adding a multiplier before the sine input. So sequence plugs into the x of the multiplier, and we add a number slider to the y of the multiplier. The default values of the number slider sometimes are not properly scaled to the project we're working on. If you click the arrow to the left of the number slider, it will expand the settings menu. The settings menu can be modified by simply typing in a new numerical value. The minimum amount that it could possibly be would be 0. The maximum amount for us would be something like 5. And the step is perfectly fine at 0.1. Then we plug our multiplier into the angle. We add a second multiplier at the end of the sine curve. We add the same multiplier to the end of the sine curve using the same settings, and then we plug that into the y input. When you hit run, you'll see that a curve has appeared in the background 3D workspace. Make sure that you can see it well enough before modifying the sliders, and then switch your manual processing over to automatic. After doing that, you'll see that the sine curve now becomes a fully functioning parametric object where the first slider now determines and modifies the wavelength, and the second slider now modifies the amplitude. After successfully completing our first introductory level algorithm, we can complete Module 2. If you'd like to continue along this path with abstract exercises, the Dynamo Primer has a library of exercises that could serve us well before moving on to an applied project. However, this course is now moving into Module 3, entitled Developing Skeletons for Parametric Geometry. Topics covered include using points and curves to construct, deconstruct, and reconstruct geometry for structural skeletons. An introduction to the use of coordinate planes and vectors and normals, and how important they are for developing an underlying structure for our project. We will fully explore the value of parametric properties in the design process for when we, as the designers or the clients, request a change further down the road in the project. And we will revisit lists in a way that requires us to custom modify the organization of the list in order to generate triangulation. The images you've just seen are just some of what you have to look forward to in Module 3 and 4. Welcome back to Module 3, entitled Developing Skeletons for Parametric Geometry. In this module, we have a number of videos that walk us through how to structure the creation of geometry in Dynamo. Using the geometries of points, lines, and planes, we'll establish a skeleton upon which we can begin to build an actual architectural structure. In this case, it's a shading structure that closely resembles the mast and boom of a ship's sails. The mast and boom skeleton will come first, and then we'll stretch a triangulated panel cover from one of the masts to the adjacent. In the previous modules, we focused our time on learning everything there is to know about what types of information Dynamo processes, and the format that it takes and how it's organized while being modified. The exercises in the Module 3 videos will apply a number of our previously developed skills. To start, our first task is to create a series of points upon which we can base our mast. The objective of this exercise is to simulate what it would be like to create a shading structure in an actual Revit environment. To do this, we'll use a model curve in the Revit workspace to map our mast generation. Beginning with a fresh Revit file, we'll go through the process of establishing a model curve on the first floor that has a simple bend. On the second floor, we can create another curve that does not necessarily have to have exactly the same curve. It should be similar and located in approximately the same position, but above the first floor curve. Now open up a fresh Dynamo file. In the workspace, the first thing we have to do is reference in the model line that we've just created. And then we can go through the process of finding a series of points along the length of the curve, which we'll use as a base point and an end point for our mast. The first component we need is called Select Model Element. Select Model Element is one of the nodes that actually allows us to tap into the Revit environment. By clicking on the Select button, you're able to move into the Revit workspace and select the model line that you'd like to reference. After doing so, the element ID should appear on the bottom gray bar of the Select Model Element component. Now, our functional component is going to be the curve.pointAtParameter node. Its description says that it gets a point on a curve at a specified parameter. When you drop it into the workspace, you'll see that the input values are obviously a curve to test and a param. In this case, a param is a numerical factor of magnitude along the length of the curve itself. So our objective is to assign a percentage numerical value or a series of percentage numerical values. However, we also need to convert the model line or the model curve into a curve itself. The component curveElement.curve will allow us to translate the element that we've referenced into a curve data type. Bear in mind that, as I mentioned before, Dynamo uses the .NET framework language for many of its commands. These are not easy to memorize, and my suggestion would be to make sure that you save all of your work so that you can reference it at a later time should you need to do some sort of a similar conversion. Now that we've connected the model curve through the curveElement.curve, and then connected the output to the curve.pointAtParameter, what we need to set up is the numerical input for param. First, ensure that your Dynamo processor is running at automatic, and connect a number slider with the values minimum of 0, maximum of 1. What you'll find is that as you move the slider back and forth, a point is now oscillating from one end of your curve to the other. In this exercise, what we want to do is divide this curve into equal parametrical subdivisions so that we can map a line from one curve to another at each point. So my objective here in this case is to create a range of numbers. So in the library, bring in the range node. Range is going to require a starting number, an ending number, and a step size. If you want 10 subdivisions, your starting number would be 0, your ending number would be 1, and your step size would be 0.1. Then plug the range output of sequence into the param input of curve.pointAtParameter, and now Revit and Dynamo will show with 11 points and 10 subdivisions along the curve. What we've just done is complete what I would call an idea. We generated geometry, we modified that geometry, and we came to a resultant conclusion that was the goal of subdividing the curve into points. Before I move forward, I want to group this together and label it with a proper name so that I can organize all the many ideas that I'm going to have to string together in order to create my boom and mast. To do so, select all of the components we just created and hit Ctrl-G. I'm going to first label what the objective of this group of nodes is, and then resize the text so that when I zoom out, I'm able to see the labels for each of these components. And this definition will get rather large, so it's advisable to use a pretty large size text. In our next video, our exploration will take us through actually stringing together the points between two curves, then further subdividing that group of curves to find a parameter somewhere in the middle to start our boom. And finally, we'll explore how to set up vectors and normals in order to generate compound transformations of geometry. The focus of this video will be to further subdivide our second curve, map a line between the points on both curves, and then place a point along those lines in order to give us a base point for the boom that stretches out from our mast. First and foremost, we've only subdivided one curve so far. For our second curve, it's as easy as copying and pasting the entire idea that we created in our previous video, and then reselecting using the other curve. As far as best practices are concerned, generally speaking, if I have geometry that's on the first floor and geometry that's on the second floor, I'll usually put the first floor geometry below the second floor geometry in my Dynamo workspace, and I'll do that now. I'll also label those groups accordingly. First floor model curve, second floor model curve. Now that we have points on the top curve and the bottom curve, my next step is to connect them with a line. Under Geometry in the library, and then under the submenu Line, you'll see that there are a couple different ways of creating a simple line type. The simple one that we're going to use in this case is the by start point end point line, which will allow us to either input a single start point and end point, or a list of points to start from, and then connect to. Plug in your first floor model curve points to the start point input, and your second floor into the end point input. What appears in the workspace is the line that stretches between the points. This is only step one of creating our base point for the boom. The next step is to create a point along this line. We have a couple of options here, one of which would be to use the same method we used in our previous step. That would be the curve.pointAtParameter. When you drop that in the workspace, one of the conversion tactics we can use here in Dynamo is that a line actually can read as a curve. A line in this essence is really just a straight curve. When it asks us for the param input, it's really a percentage of the line's height. For instance, if we add the number 0.5, our boom start point will be placed at exactly halfway across the length of our mast. If we go to 0.25, it'll start a quarter of the way up, or if we go to 0.75, it'll be 3/4 of the way. And that applies even if the lengths of our masts are different. The other option we have is to use the curve.pointAtDistance node. The description of this node reads that it gets a point at a particular arc length along the curve. A length is essentially a distance measurement as a numerical input. In this particular case, we set the slider's properties to be 0 as a minimum, and somewhere around the height of our second floor at a maximum. As we move the slider back and forth, you'll be able to see the point moving up and down along the length of your line. And I'd like to give you just a glimpse at what is most powerful about this. In Revit, if I'm to modify the location of one of my model curves and sort of lean the entire assembly forward a little bit, you'll see that the lines now remap to the new location of the model curve above, and my parametrical relationship, my point along that line, still maps properly to some parameter directly along the line, even though the length of these lines has now increased. Before I move forward into the next segment, I'm going to return that model curve to its original position, approximately above my first floor curve, and I'm going to select which option I'll choose. At this point, it really doesn't matter if you use the curve.pointAtParameter or the curve.pointAtDistance. It's up to your choosing. For me, I'll use the curve.pointAtParameter so that I can keep my point at a halfway mark of all my lines, regardless their length. The last step is to group and name whichever idea I move forward with and eliminate the extraneous information. So I'll delete my curve.pointAtDistance along with its number slider, and I'll name the group for curve.pointAtParameter midpoint. As we progress through the next video, we'll start to work with planes and vectors, and understanding directional translations and modifications in a Dynamo model. In order to create the boom arm that extends from the point on the mast, we need to first learn a little bit about some terminology that's going to allow us to create a parametric rotation about that point. First and foremost is the idea of a plane. A plane is a two-dimensional reference surface. Any points that are mapped onto this plane would be what is considered planar, which, when looked at in a digital environment, is typically represented by an X and a Y axis. This goes back to your basic math education, where we referred to this as the Cartesian coordinate system. The Cartesian coordinate system is basically made up of 90-degree angles, within which we can calculate mathematical formulas to derive more complex forms. The most simple components of the Cartesian coordinate system are the three basic axes. The x and the y plane are typically what you would look at if you look down on a grid. The x direction is traditionally represented in the east-west axis. The y-axis is 90 degrees rotated from the x-axis. Likewise, the z-axis is the one that is rotated off-plane 90 degrees from the y and x-axis. This is what we mean when you hear about 3D projection, 3D movies, 3D modeling. The third dimension is the geometry that's created in the z-axis. The other terminology we must understand is that of vectors. A vector typically has two components. It's made up of direction and magnitude. When considering the structure of a plane, the x, y, and z axes can also be considered as vectors. In common practice, we use the x and the y axis as a reference for perpendicularity. When we align the x and the y axis to a surface, for instance, the z axis then becomes what's called a normal. In a simple planar application, the normal is the z-axis. It's the 90-degree rotated directional vector from any point of origin on that surface. However, a surface normal can also be applied to a warped or curved surface. In this application, the normal is considered the perpendicular vector to the tangent plane of any point on the surface. Back to our model for a moment. How we're going to use this to our advantage is to align one of the axes of a simple plane to the masts that we've generated. From that, we can use the normal of that plane in order to create a rotator. This will allow us to create a boom arm that rotates about the point that we've established on the mast. We're essentially creating a pin connection at the middle of our mast so that our boom can be raised and lowered on command. This particular exercise is a great example where you would want to begin with the end in mind. For instance, I know that I want to work with a plane. Expand the geometry menu in the library and expand plane. Plane has a number of options. Our task is to choose which one is going to provide us with the right rotator that we need. Without going into all the different possible selections, I do know that I need to create an axis. And I'm thinking that my axis will probably be built off of the x and y axes. So I'll use by origin, x-axis, y-axis. This node is going to require an origin point or list of origin points, as well as a vector that defines the x-axis and the y-axis or list of axes for these planes. Our origin is going to be the list of points that's generated from our previous video, the curve.pointAtParameter. Or if you chose curve.pointAtDistance, you can use that as well. To figure out how to get a vector from the information I currently have, I'll simply type in plane and look at my options. When doing that, I see that I have a series of generation tools, and I have a couple of action tools. A few of them read plane at parameter and plane at distance. Using the plane at parameter node, when dropped into the workspace, it asks for a curve and a param. So ideally, I'd be able to plug in the curve that I'm trying to map this to, and then plug in the subdivision param and map all of the planes to it. However, when this is plugged in, what happens is those planes are aligned to whichever curve I choose. In this case, I chose the top curve, and it looks like it's aligned properly. If I rotate around, it looks like the y-axis is approximately aligned with the vertical mass that I've generated. However, if I move now my model curve to a tilted position, the plane now does not rotate. It will move with it to the new position, but it does not rotate out of the XY orientation. Vector by 2 points is going to allow me to insert a list of points to start with and a list of points to end with, and all it does is create a list of vectors in the direction from one point to another. Our start point will actually be the first floor list of points that it generated, the subdivision points that we created on the model curve. The endpoints will be the ones at the top of our mast, so that would be the second floor list of points that we generated. Then we plug vector into x-axis, and it won't be complete until we actually create our y-axis. Y-axis is going to be slightly different. For this, we're going to use the curve.normal@parameter node. This one is special because it actually grabs a vector perpendicular to the curve at a specified parameter. What that means for us is if we place a plane on one of the points of our mast, either the base or the top, we can rotate it laterally so that it matches the perpendicular plane to each of the params through the curve rather than aligned to the curve. Using the curve output from the second floor, we'll connect the curve and the same associated params, which will generate a vector that's perpendicular to that location, perpendicular to the curve itself, the model curve we've generated. When you plug this vector into the y-axis input, a plane will be generated perpendicular to the orientation of the points on the curve, as well as aligned to the angle of the curve should we move our model curve at the second floor. As a fair warning to those of you who are beginning users, there are tens if not hundreds of ways that you can modify these particular types of components, whether it's a plane, a vector, or a normal. One of the best things you can do is open up the geometry tab in the library and start to read the descriptions of the different types of planes and vector options available to you. Before proceeding, make sure to group these components together and name them. I'll name these mast-aligned planes. In the next video, we'll establish the skeleton for the boom arm and create a mathematical operator that will give us a degree of variation in that length. In this video, we're going to quickly create the boom arm itself. Beginning with the end in mind, we'll create a line in the library under the Geometry tab, expand line. What we'd like to do in this case is to use the vector that we've generated and then define how long the arm must be in each case. The line by start point direction length will allow us to establish the start point, input a direction vector, and input a length as either an individual number or as a list of variable numbers. The start point is going to be the point along our vertical mast that we generated in video 2. Using either the curve.pointAtParameter node or the curve.pointAtDistance node, depending on which one you chose, use the point list output to connect to the start point input. For direction, we have to use a vector that we generated in our previous video. However, rather than creating a vector, what we generated is a plane that has an x and a y and a z axis. Close the line menu in the library and open up the plane menu. Towards the bottom, under query, we have normal, origin, x-axis, and y-axis. Query is going to allow us to isolate any of these components from a plane. Unless some of your connections are a little bit backwards, you should be able to use the y-axis option and connect that from the plane.byOrigin x-axis, y-axis. When you plug this into the direction and then plug in a numerical value for the length, you'll see that you're able to create the boom arm, but it might not necessarily be what we want. So with our objective to rotate the boom arm around that point, we have to insert a separate connection that's going to rotate that vector before we plug it into the direction input. Easily enough, in the library, if you search for vector rotate, the vector.rotate node is going to accept the y-axis vector. In this node, the origin is actually asking for a plane rather than a vector to rotate around. But the thing to note is the origin about which you rotate is going to be the normal of the plane itself. So the x-axis, y-axis plane has a z-axis that's going to act as our rotator. In the background 3D preview, you should be able to see a gray line that extends along the z-axis of each of the planes that you previously mapped. This is the axis about which we will rotate if we plug in those planes. So plug the planes in now, and next, insert a number slider. The number slider is going to go from 0 to 360 to allow us to do a full 360-degree rotate about that axis. Finally, you can plug in the vector to the direction of our line by start point direction length. And as you move the number slider back and forth, you'll see the rotation happening in real time. Now at this point, we have a functioning boom arm. The length of that boom arm still is static. So what I'd like to do is to create a degree of variation in the length of that boom arm. To generate the list of lengths that we need, we can use range yet again. Range is going to require a starting number, an ending number, and the steps that are required in order to get to that ending number. Now we know we have 10 subdivisions, which means we have 11 numbers. If we have a number from, say, 5 to 10, we need to be conscious of how many subdivisions we can create. So 5 to 10, if you divide that by 0.5, will give us the 10 subdivisions or 11 numbers that we require. Depending on how big you drew your model lines, your sizes might vary slightly. To give you a sense of roughly how big my curves are, they're approximately 30 feet in length, which makes a 5-foot minimum length for my boom arm and a 10-foot maximum length for my boom arm rather appropriate. Before moving on to our 5th and final video for Module 3, be sure to group and name these components. I'll simply group and name them boom arm. The video tutorials going forward will be a focus on how the information should be passed through in order to combine lists in an irregular fashion. By this I mean, if you triangulate the connections from one mast to the other boom arm, a list will have to be shifted and reduced in order to connect only 10 of the 11 generated points between the arms. And finally, we'll finish our Dynamo development by mapping a surface between the points that we've developed in our skeleton. The challenge of this section of our exercise is that we have to connect a surface from an isolated mast and boom arm to a point on an adjacent boom arm. The method that I've chosen in the Dynamo environment to represent the surface is a surface created by a loft. A loft essentially stretches a surface between two lines or edge curves. To keep it simple here in the Dynamo environment, we're going to create a line from the top of your mast to the endpoint of that mast's associated boom arm. The next step is to stretch a line from the mast's endpoint at the top to the adjacent boom arm endpoint. In developing this definition, I'll start with the generation of the lines. I know that I have the ability of creating a line from a start point and an endpoint. Dropping in the line by start point endpoint, we see that we need the start point being the mast endpoint at the top, and I'm going to establish that as the start point for both of the lines I'm generating. That way, all I have to do is isolate the endpoints in two different ways. To get the endpoints at the end of our boom arms, we have to use the curve.endpoint component. We can plug the line output that we generated for our boom arm into the curve input for curve.endpoint. And what it gives us is a list of all of the endpoints at the end of our boom arm. So now our very simple solution for line 1 would be to connect the point output of curve.endpoint into the endpoint input of line.byStartPoint endpoint. This will generate the first and simpler line that we require in order to create the loft. To get a line that stretches from our mast endpoint to the adjacent boom arm endpoint is a little bit more complicated. We need to use what's called list.slice. And the objective of list.slice is to allow us to segment the list to take off the first or last point in the list of points. Working backwards from list.slice, we need to give it, obviously, the list of points that it's going to modify, which we can take from curve.endpoint. Then I'll describe the requirements for start, end, and step. Start says index to start the slice from. That means if you look at your list via a watch panel or by hovering over the node, you see that the list starts from an index of 0. What's important here is that we set our start point at a value of 1 if we want to eliminate the first point in the list. Similarly, our step is only going to be a value of 1. For the end input, we have to define where to end our slices. In this case, the end of our slices is going to be the total amount that we have in points. To find the total amount we have in points in a parametric automated way, we can use the list count node, which will measure the list of points and output the numerical count of how many points exist in that list. If you plug a watch node into the curve.endpoint and plug a watch node now into the list.slice, what you'll see is that the index value of 0, the point at the beginning of our list, is no longer present in the list that we generate at the end of list.slice. So now when we plug this in to our second line by start point endpoint into the endpoint input, now we have our second line generated, and it stretches from the mast endpoint at the top to the boom arm endpoint at the end of the boom arm on the adjacent boom arm and mast construction. Moving forward, our next objective is going to be to loft the two surfaces together. However, we have a problem that we must address first before we can loft the edges together. Plug a watch panel into the end of the line by start point endpoints. What you'll find is that the count of lines coming from one totals up to 11 lines. The count from the other totals up to 10 lines. This poses a problem for us because when we try to loft or connect the list of 11 edges or lines, it'll give us an error because it's trying to connect 11 lines to just 10 lines. We have to go through the process now of eliminating the 11th line so that we can get a match of 10 lines to 10 lines. The difference here is that when you use list slice, now our count is slightly different. We're no longer trying to cut out the first in the list, we're trying to cut out the last in the list. So in this case, the list input is going to be the list of 11 lines. For our start point, we're going to start from 0. However, our end point is going to be a number that is 1 less than the count of lines that we have. Rather than just typing in the number 10, I'm going to use a subtractor with a list count so that should I ever decide to change the count of masts and booms that I have, it'll be parametrically tied to that amount. To do this, I need to connect a list count node to the end of my list of lines, and the count should read 11. In the library, if you expand the operators menu, you'll see a list of simple mathematical operators. In some cases, it's basic arithmetic. The minus symbol, if you bring that into the workspace, the description says that it simply subtracts y from x. So if I plug in my count to the x value, which is 11, and I subtract a number of 1 using either the code block or a number input, I'll get a consistent value of 1 less than the maximum count of my list, which I'll take my variable output and I'll plug it into the end input of my list slice. So now in this case, the key component of list slice is the step, and the step here still remains 1. So if we take stock of what we have, at this point, we have a list of 10 lines that we've reduced from the full count of 11, and we have a list of 10 lines that we mapped from the top of our mast to the adjacent boom arm endpoint. At this point, we can jump forward to our loft component, but as a warning, in the library, one of the things to be aware of is that loft is a pretty popular command. We have many different kinds of lofts. Some of them are for surfaces, some of them are for solids or poly surfaces. What you need to be aware of is that what we're creating here is a simple surface. The by loft node that you see at the top creates a surface by lofting between input cross-section curves. When you input this into the workspace, you'll see the only input available to you is cross sections. And it's a singular input, so it doesn't allow us to connect one item in and then connect a second item in. That tells us that what we have to do is create a list of lists, which, if you recall, uses the list.create node. Drop the list.create node into the workspace and plug in the list slice, and then add another input and plug in our other list of lines. What you'll find if you put a watch node on the end, or if you just hover over and look at the list that you have below, is that your list of lists is built out of an index list 0 and an index list 1, within which 10 lines live in each. Recall back to the exercises we did with concatenation, and when we created sentences, we were not able to concatenate our first parent list to our second parent list. We had to restructure them so that index list 0, index item 0, is paired up with index list 1, index item 0. We have a simple tool called list.transpose that will do that for us automatically. Bring transpose into your workspace. Plug the list.create output into your list's input for transpose. Now, via a watch node or by hovering, you can see that our lines are now paired up appropriately in sets of 2. When plugged into the cross-sections input of surface.byLoft, you'll have a surface generated by the Dynamo workspace that illustrates the triangular shading stretching from one boom mast and arm to the next. And the real power of this is that all of this skeletal construct is fully parametric. We have the ability to rotate our boom arm around that base point in 360 degrees. So if we need our panels on the other side of our curve, we can simply flip it over about 180 degrees and it'll move to the other side. Additionally, we can fine-tune it just by going up and down a couple of degrees in order to create more or less shading. This gives us great power in the design process because now we really only had to build 2 model curves, and we can use a series of sliders and adjustments in order to find the perfect design for our shading structure. In the next module, we'll briefly look at what it takes to make a geometry live in the Revit environment. With this being the course's primary modeling exercise, my suggestion to you would be to go back to the beginning, rebuild this definition, and try to change it slightly. A good exercise to go through would be to try and switch the direction of your panelization. You can also try panelizing a triangle in between your vertical masts. Welcome to Module 4, entitled Generating Form for Revit Use. In this module, we'll look at the direct import method of publishing geometry from the Dynamo user interface into the Revit modeling environment. It's important to remember that the geometry we are creating in Dynamo is not live in Revit. If I was to close my Dynamo window, make sure to save your file, you'll find that the information we've generated that shows in blue when Dynamo is open is gone, and all we are left with are the modeling curves that we created at the beginning of this exercise. Reopen Dynamo and reopen the file that we were previously working on. Make sure to run if you're operating in manual, or if you're in automatic, it'll automatically update your Revit model space to show the geometry from the file. Now, when considering publishing the geometry from Dynamo to Revit, we must know that there are two primary environments that Revit can create geometry in, the first of which is the massing environment. The massing environment is a space where we can explore form generation and not get into detail by assigning any kind of system families such as your walls. And the modeling environment. The modeling environment is where the bulk of the documentation that we do in Revit happens. It's where all of our system families and our custom families live and produce information for our drawings. Our goal in using the direct import method is to format the Dynamo definition to use components that will automatically update in the live Revit modeling environment. This is what I refer to as the direct import method. Since the shading structure is relatively simple in how it's built, we will use a basic adaptive component in order to stretch a triangle across the shading structure panels. We will also use the out-of-the-box standard Revit structural framing components to map to the mast and the boom arm in order to support the shading panels. Like I mentioned in the introduction to this assignment, we're not getting down into the level of detail where you'll see hardware that's attaching the panel to the structural members. However, we will take into consideration how the panels are terminating at their connection points. Like all other smart BIM families, the panels will be created by a material that has thickness. Before I produce the adaptive component side to publish into Revit, I'd first like to show you why we decided to actually stretch a surface across from two lines rather than using an adaptive component assigned to 3 points only. The reason for this is that in the massing environment, one of the very important features that we can use is called thicken, and it's found by searching in the library for surface.thicken. Its description says that it thickens a surface into a solid, extruding in the direction of the surface normal. It requests the input of a surface, which we've generated, and a numerical thickness. So when it's connected to the surface of our panel, and we present it with a slider, you'll be able to see that the thickness of the panel is now readily parametric. However, for us, what we're going to use is a 3-point adaptive component. With the files provided to you as a part of this course, you'll see a family that's called Shade Adaptive 3 points. Go into Revit now, and under the Insert tab, click Load Family. Navigate to the location that you saved this file and load it into your Revit file now. We're going to use this family in the Dynamo user interface to apply parametrically to all of the panels that we've generated. Now back in Dynamo, the node adaptive component.byPoints. If you search in the library just for the term adaptive, you'll see a short list of adaptive component nodes. The one we're looking for is called byPoints. It says that it creates a list of adaptive components from a 2-dimensional array of points. That means that however many points you have, they must be planar. Luckily for us, we created triangles, which, no matter where they land in space, create a planar condition. It's going to request a list of points and a family type, and this is the start of where we're going to work backwards to get to our goal of assigning an adaptive component. First and foremost, the family type is the simpler of the two, by far. In the library, search for the term family, and you'll see that up at the top, family types should appear. When you drop it into the workspace, it has a family type output, which should directly relate to the family type input of adaptive component. Under the pull-down menu, you should be able to search for the Shade Adaptive 3 Points family. Now for the hard part. What we have to do is isolate all of the points of each panel, but in their appropriate list configuration. What that means is the list of points at the top of our masts has 11 points on it. We'll have to subtract the last point since it's not used by the final panel. We'll also have to take two lists of our boom arm endpoints, one of which is going to stop one short, the other is going to begin one later. In order to combine all of these lists together, I'm going to use a list.create node. The first item that's going to be plugged into my list.create node is going to come from the list of boom arm endpoints. More specifically, it's going to be the list of endpoints that stops one short. To do this, we already have all of the components that we need readily built in the previous exercise. It happens to be the list.slice that we used to delimit the list to connect our line for the panel. If you look in the last group that we developed, the list.slice with a code block attached to it that says 0 and 1 with a subtraction math operator. Follow that all the way back to the list count node and copy that down to a location that's adjacent to the curve.endpoint that you originally plugged in. What we're doing is moving that unit a step backwards before we created the line. And now, rather than adjusting the list of lines, we're actually adjusting the list of endpoints that generated the line instead. So connect the curve.endpoint node to the list input of list slice. Also, connect the curve endpoint node to the list input of list count. The list generated should plug into item 0 of our list.create for the adaptive component. The next item is far easier. You'll see that we've already generated a list slice off of the curve.endpoint. Back in the previous exercises group, there's a second list.slice that does not have a mathematical operator. We'll use this tiny little segment in order to isolate the list of boom arm endpoints that begins one later. We don't have to copy it. All we have to do is plug in the output from list slice into the item 1 input of our list create for the adaptive components. And finally, the last input is going to be another copy of the list slice with the negative or subtractive mathematical operator. However, this time we're going to plug in the list of masked endpoints so that our masked endpoints stops one short. What this will do is create a connection of 3 points from your masked endpoint to its associated boom arm endpoint to the adjacent boom arm endpoint. And this is the configuration of triangulation we've been using all along. Finally, once that's complete, if you look at the list create output, you'll see that it combined the lists into a list of lists. We'll need to transpose this list into something that associates the 0 index of each list into a pack of 3. Now plug it into your adaptive component .byPoints and check your Revit workspace. The adaptive component now lives in the Revit modeling environment, and when you click on it, you can see exactly where point 1, point 2, and point 3 are being mapped. Additionally, by going back to the slider that determines the rotational position of our boom arm, we can now parametrically modify the configuration of our shading panels in real time. In the next and last video of this course, we'll explore how to assign a structural framing member profile to the lines of our mast and boom. And finally, we will adjust the termination of our panel where they overlap in a custom condition. To place the finishing touches on our shade structure canopy, we'll have to assign a structural framing member to place on our mast and on our boom. In Revit, under the Insert tab, click on Load Family. In the Imperial Library, the folder called Structural Framing is where you'll find the various types of structural members we typically use in the architecture profession. In Steel, the steel member that I will use is a hollow structural tube. So under HSS Round Structural Tubing, click that and open. Revit will list all of the types and various sizes of that particular structural member family that you can load. In this case, I'll use an HSS 6 by 0.25, which is a 6-inch round steel column with a 1/4 inch thickness to the tube. And I'll use an HSS 4 by 0.25. Click OK to load the families. Now's the part where we work backwards. In the library, expand Revit. Under Elements, you'll see that there's a menu called Structural Framing. The Beam by Curve component will ask for the structural framing type to assign to a particular curve. It also asks for a level that it should be associated with. Now the level is purely referential so that it can place the endpoints of the structural component in space. For our mast, the first curve we're going to insert is the line that we generated to create the mast. This would be the line that we plugged into the curve.pointAtParameter or curve.pointAtDistance, depending on which one you chose. Back up to the Revit Library menu. Under Selection, we have the opportunity to select a couple of things that we need. The Levels component, when dropped in the workspace, will have a pull-down menu that should list all of the levels that have been created in that particular file. The other one we would want is the Family Types. Family Types has another pull-down menu that lists all of the families that are loaded into your Revit model. In this case, the HSS Round Structural Tubing HSS 6 by 0.25 is what we'll select. Then plug Family Type into Structural Framing Type. Once all three connections are made, in the Revit workspace, you'll see that the tube steel now appears in the position of our mast. Now the boom arm is incredibly simple. All we have to do is copy and paste this entire configuration over and then override the curve connection from the line output that we generated for our boom arm. So altogether, we managed to create the structural skeleton for the shading panels in a matter of minutes. Now, take a quick look at the detail connection between two panels. There's a slight overlap with the adaptive component that we'll have to address if we want this particular configuration to look somewhat convincing. If you have a completed definition such as this, but there's a custom modification we have to make, it's easy enough to just go back and override a change in the middle of the sequence or definition. In this case, I'm going to move the point of connection for each of my panels along the z-axis, the world z-axis, which means it's just going to go straight up and down. And then I will plug that point into the list create for the 3-point adaptive component panels inputs. As a general suggestion, when you don't know the name of a tool in order to accomplish a task, the library allows us to search by keyword. So if we simply type in move, and we think to ourselves, I want to move a point upwards. In the library, you can read the descriptions of the tools that pop up. And the one that catches my eye is the Translate Direction and Distance. It allows us to plug in a geometry, which can be points, lines, planes, any kinds of geometry that we create, as well as a direction, which I can determine as the world z-axis, and a distance, which is a numerical input, which can easily be a slider. The geometry we're going to plug in is the list of points that we plugged into the list create for our adaptive 3-point component. However, we're going to use specifically the input that determines the connection to the adjacent boom arm, and that would be this one. For the direction, I know that I'm going to try to move it in the world Z axis. So in the library, if I simply type in Z, the very first component to pop up is the Z-axis component, and this is the world Z-axis. So the geometry will only move upwards in my file's model space. And then I plug in a number slider to the distance input, and I can set that number slider to something that's reasonable. In this case, I'll go anywhere from 0 to, say, 2 inches, and I'll leave it rather small, maybe 0.5 for now. Then I plug that geometry to override the existing connection. And now you'll see that when you move the slider back and forth, we can very fine-tunedly adjust the overlap and how far apart these panels are at their connection point. What we've just created is a highly adaptable skeleton. It's a structural framework where we can utilize the strongest parts of the Revit user interface, assisted by the power of Dynamo visual programming. Using the direct import method, we have full flexibility to post-produce this particular model into something that we can use with all the other features of Revit, for instance, the rendering features or the construction documentation features. The limits are pretty endless with Dynamo, and I hope that you'll explore it more. Should you have a further interest in Dynamo and need some assistance while trying to learn more, the user group forum at dynamobim.org is an incredibly valuable source. Also, remember that the Dynamo Primer is a great resource to develop a foundational knowledge of Dynamo's inner workings. And finally, if you like to explore in a hands-on environment, under the Help menu, the samples will allow you to explore some of the more powerful tools in Dynamo. Thank you for taking the time to watch Visual Programming Introduction with Dynamo and Revit. I greatly look forward to seeing all the wonderful work that you produce in the near future.